Part 2 moves from one intelligent vehicle to many connected agents. The focus is cooperative perception, sharing complementary viewpoints across vehicles and infrastructure. Every year, 1.19 million people die in road traffic crashes worldwide. That is the equivalent of a large aircraft crashing every single hour. 94% of these accidents involve human error, driver distraction, impaired judgment, failure to see a hazard in time. Waymo recently released a large-scale safety study comparing its autonomous vehicles to human drivers in equivalent traffic conditions. The result, an 80% reduction in injury-causing crashes. This is a meaningful number because it comes from real-world deployment, not simulation. It demonstrates that the technology works at some level and raises the question of how to make it work everywhere for all agents. Before multi-agent systems, let's examine where single-agent autonomous driving had arrived by 2024. The trajectory is clear. PNP-Net introduced joint perception and prediction using convolutional networks and recurrent modules. Gameformer brought interactive prediction into planning, modeling other agents as game theoretic players. UniAD unified the entire pipeline into a single query-based end-to-end model optimized jointly. Diffusion Drive uses a diffusion model to generate trajectory distributions with principled uncertainty representation. Each step reduced the handoff cost between modules and improved joint optimization. But performance on benchmarks is not the same as safety in the full physical world. Here is the fundamental limitation that end-to-end improvements cannot fix. A single LiDAR cannot see around occlusions. If a truck is blocking the view, there is no signal to process. The only solution is complementary information from a different vantage point. When two vehicles share their perception data, the combined field of view fills in the precise occlusions that each individual agent experiences. The cooperation is geometrically additive. What one cannot see, the other can. The coverage is not just the union of two circles. It resolves the specific blind spots created by the geometry of the scene. The research community recognized this potential early. Over the past several years, a series of progressively more capable cooperative systems were built, and along the way, two critical gaps became apparent. The datasets have similarly matured from the purely simulated OPV2V to DAIR-V2X with real infrastructure data to V2X-real, the first large-scale real-world dataset covering both V2V and V2I scenarios. But across all of these contributions, two critical gaps remained open. Gap 1, task scope. Every prior method addressed cooperative perception as a detection problem. Classify objects, output bounding boxes, stop there. How cooperation benefits the full automation chain, prediction and motion planning was unexplored. Without temporal context, prediction is severely limited. Gap 2, data. Existing datasets lack the sequential, time series structure that temporal fusion requires, and no dataset covered all V2X collaboration modes simultaneously: vehicle to vehicle, vehicle to infrastructure, and infrastructure to infrastructure in one place at scale. The gaps point to three concrete research questions that any serious V2X system must answer. What to transmit: raw sensor data, detected objects, or intermediate feature maps? Each trade-off has implications for bandwidth, accuracy, and latency. When to transmit: a single frame, a history, and how do you decide when agents are too far apart to communicate efficiently? How to fuse: once data from multiple agents arrives at the ego vehicle, how do you integrate information from different viewpoints, timestamps, and sensor modalities into a single coherent scene representation? V2X PNP, Vehicle to Everything Spatiotemporal Fusion for Perception and Prediction, addresses all three questions in a unified end-to-end framework presented at ICCV 2025. What to transmit? V2XPNP evaluates all three fusion strategies, early, late, and intermediate, each with a temporal dimension. When to transmit? Using a one-step communication strategy. When agents are within range, they transmit their full history in a single exchange. Temporal attention then compresses this multi-frame history into a single frame representation before transmission. How to fuse? Two complementary modules. Temporal attention aggregates the motion history of each individual agent. Spatial attention integrates information across different agents at the same time step. To support the framework, the team built the first real-world sequential dataset covering all V2X collaboration modes simultaneously. The setup includes 2 connected automated vehicles and 2 infrastructure nodes at a real urban intersection. Building the framework is one thing, training it is another. This chart shows the core difficulty. Orange dots are one-time training attempts on the full multi-agent, multi-frame, multitask system. They fail outright. Blue dots are the result of carefully sequenced manual training, 4 separate stages over 120 epochs, requiring expert judgment about when to transition between stages. 2 root causes: initialization sensitivity. A complex architecture with temporal, multi-agent, and multitask dimensions converges to a bad local minimum when trained from random initialization. Gradient conflict, detection, prediction, and planning objectives pull the model's weights in contradictory directions. Standard SGD has no mechanism to resolve this. TurboTrain solves both problems with a 2-stage pipeline. Stage 1, masked pre-training. Stage 2, gradient balancing. The result, 45 epochs instead of 120, higher final performance than the manual 4-stage process, and no requirement for human expertise to manage the training schedule. Perception and prediction enable the vehicle to understand the scene. Planning requires using that understanding to make safe decisions. And this is where interpretability becomes critical. RiskMap introduces an explicit risk map as middleware between the learned representation and the planner. The risk map is a probabilistic spatial temporal representation of danger, a map in which each cell encodes the likelihood of a hazardous event at that location and time. A learning-based model predictive controller then uses this risk map to compute a safe trajectory. 3 problems, 3 solutions forming a complete stack. V2XPNP establishes the foundation, a real-world dataset covering all V2X modes, and a framework that answers the what, when, how of spatio-temporal cooperative fusion. TurboTrain solves the practical training bottleneck. Pre-train then balance cuts training from 120 to 45 epochs without human stage management. RiskMap extends the stack towards safe planning, interpretable middleware that turns learned scene understanding into a verifiable planning interface. All 3 systems have now been built. They work in simulation and on benchmark datasets, but deploying them in the real world requires something we have not discussed: the hardware, the sensors, the calibration, the localization infrastructure, and the data collection pipelines that make real-world training and operation possible. The gap between a simulated cooperative perception system and one that runs on a real intersection is significant, and it is exactly the gap that Part 3 addresses.